Let's now start to build up the periodic table and see how we can use this to write our electron configuration. So remember that the proton number is the same as the number of electrons in the neutral atom. So here hydrogen has one proton, and then what we do is go across the periodic table to the next element along, which is helium, which has got two protons and therefore two electrons. We then skedaddle back to the next energy level. So if we number this the first energy level here, then the next element along is going to be lithium, which has got three protons, hence three electrons. So we keep winding our way back. So there's lithium, beryllium, and then we get to this element here, which is going to be number 5, number 6, 7, 8, 9, 10, and then again back to the next energy level, which is energy level number 3. So as you saw from my video where we were filling up energy levels, this number here is the number of energy levels that the electron is going to go into. But because of the D is always overlapping with the 4s, we'll give this energy level the value n minus 1. So electrons going into this element here, into D1, the electrons would start going into the third energy level. We'll make that more apparent later on. So the D block, remember, is the energy level, but you take a 1. And the rest, so for the S block, and for the P block, and for the F block, it's exactly the same. And don't worry about the F block. So that's energy level 5, 6, 7. So we can start to fill up the numbers. And remember, you'll have this periodic table in front of you. So that's element 12, and then 13, 14, 15, 16, 17, 18, and 19, and 20. So let's write the electron arrangements out for the first 20 elements. You can get the symbols from your periodic table. So we saw that electrons go into the lowest energy level first, and since hydrogen has only got one electron, it's going to go in the first energy level, it's going to go into an s orbital, and it occupies that singly. So we write that out as 1s1. If we were to represent the orbital as a box, we show that as an electron spinning on its own direction with a single-headed arrow like that. Then helium is going to be, the electron's going to go into the first energy level, into an s orbital, and it's forced to pair up, and therefore we would write its electron configuration as 1s2. The next element has got 3 electrons, and now the first energy level is full. So that 1s orbital has got 2 electrons in it, and now the electrons are going to be forced to go into the second energy level. So the electron arrangement is going to be 1s2, and the electrons are going to have to go into the 2s, and it's going to occupy the orbital singly, so it's going to be 2s1. So that follows on, and we can do that for, let's go up to all of the 20 elements. So 1s followed by the 2s, then electrons go into the 2p, then they go into the 3s, and then they go into the 3p. So remember, there is a maximum of 2 electrons allowed in an s, 6 electrons allowed in a p, 2 electrons allowed in an s, 6 electrons allowed in a p. And then remember that electrons go into the 4s before they fill up the 3d. So let's just take a random element from the periodic table. I'm going to choose calcium. Before I write out the full electron arrangement, what I can do is I can find the position of calcium. And I know that its outer electrons are going to be in the 4s subshell because it's in energy level 4, it's in the s block, and it's in the s2 group. And therefore I know its outer electron arrangement is going to end in 4s2. And therefore it's really easy for me to write the rest of the electron arrangement as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So I can write the electron arrangement out without even counting electrons. Now we know it's got 20 electrons, and if we add them up, 2, 4 and 6 is 10, 12, 16, and 18 and 20. And that is a surefire way of knowing you're going to get the right electron arrangement by simply looking at the element in the periodic table. Let's try a more difficult one. How about arsenic? Arsenic has got 33 electrons. Let's identify where it is in the periodic table. Well, the outer electrons are going to be in energy level 1, 2, 3, 4. So its outer electron is going to be in energy level 4. And the outer electrons are going to appear in a p orbital, and they're going to be p3. So already we know the outer electron arrangement and the outer electron configuration of arsenic. And then the rest is easy, we simply fill them in. Let's try that. Since arsenic is in the 4th row, its outer electrons are going to go into the 4th energy level. And it's in the group P3. So we know that arsenic's outer electron configuration is going to be 4p3. And then all we need to do, as usual, is to fill in from the start. 1s2, 2s2, 2, start again, 2p6, 3s2, 3p6, after the 3p, that's the 4s2, 3d10, 4p3. Add all of those electrons up and they come to 33. So you're always going to get the outer electron configuration correct. You should now practice writing out your own electron arrangements for all of the elements all the way to period 4. Now you'll realise it is a big pain in the neck to keep writing those electron configurations out, so we're going to use something called the noble gas or the condensed noble gas notation. So if we choose an element at random, again let's choose, for argument's sake, silicon here. Silicon is in period 1, 2, 3, and we know therefore it's going to end in 3p2. And we write out the full electron arrangement for silicon, which is 1s2, 2s2, 2p6, 3s2, 3p2. If we move back to the nearest noble gas, if we go backwards to the nearest noble gas is neon. And neon has the electron configuration 1s2, 2s2, 2p6. And therefore, we can simplify the electron configuration by putting brackets around the symbol for argon, because it's isoelectronic with argon, and 3s2, 3p2. Let's choose another element. This time, let's choose a noble gas. Let's choose a transition element. Let's choose cobalt. We can see here it's in the column D7. And remember, for the energy level, it's not 4, it's 4 take away 1, so it's going to end in 3d7. So cobalt is going to end up as 3d7, and remember 4s2 for the, because we're going here to 4s2. The nearest noble gas, we move backwards, so we go all the way along and all the way back, is going to be argon. So the electron configuration for cobalt is going to simply be argon, square brackets, 4s2, 3d7. That is the noble gas or condensed notation for the electron arrangement for cobalt.